So then today we are going to start with section 8.3, which is trig substitution. So this is another way to solve, to do integrals. So integrals of a certain form. I love trig substitution. It's like one of my actually favorite techniques of integration. Most people do not. As a matter of fact, like my husband, who also teaches mathematics, when I was passing our daughter off to him and stuff, and he was like, "Oh, what are you teaching today?" I was like, "Trig substitution." He's like, "Ugh," and I was like, "I love it," and he's like, "I know, you're weird." So anyway, so not everybody loves it, but I like it because it's very kind of obvious when you need to use trig substitution, and there are a set of steps, and as long as you follow the steps, then everything just comes out super nice. The thing that people don't like is that trig substitution takes a problem that has no trig in it and actually turns it into a problem that has trig in it. So if you were kind of like, oh, I wish you had done more examples of the stuff from last class, have no fear, because all the problems we're going to do today turn into problems from last class. And then we will practice even those problems even more. So trig substitution is used for a very specific integrals that have a very specific thing in them. And so and we're going to kind of write that down. So it's used for integrals that have one of the following things. They either have in the integral a squared minus x squared, they have an a squared plus x squared, or they have an x squared minus a squared, and we can't use regular substitution. Okay, so they're integrals that somewhere in the problem, oftentimes, not 100% of the time, but oftentimes these are under a square root sign. So you might have the square root of a squared plus x squared, or the square root of x squared minus a squared. And we can't just use a regular substitution, okay? I think sometimes, and I think this was seen on the test, when you learn a technique of integration, sometimes you begin to think, oh, every single problem I can use this technique of integration on, right? So you want to be careful. Just because we're learning trig substitution does not mean every single integral that has an a squared plus an x squared is a trig substitution integral. So we want to be a little careful about that. Basically, the method that we're going to do, so the method is depending on which of those forms we have. So depending on the form, we will make a substitution. All right. And so we're going to make a little table here. Here's our forms, and here's what we're going to substitute. So if we have a squared plus x squared, we are going to substitute and let x be equal to a tangent theta. If we have a squared minus x squared, we're going to let x be equal to a sine theta. And if we have x squared minus a squared, we're going to let x be equal to a secant theta. Okay, so we're substituting one of these three things, right? Sometimes people ask me, well, how come you're never substituting cosine, or you're never substituting cosecant or cotangent, right? So the reason we don't substitute them is because, remember, things are paired together. So sines and cosines are paired together. Tangent and cotangents, right? They're related to each other. Secants and cosecants are related to each other. So these are the three substitutions that we make. And basically what's going to happen is we're going to identify what we need to substitute, and then we're going to carry out the substitution, and it's going to turn our integral that we couldn't have done before into something we now can. So let me do an example, and I think that'll help kind of make this a little clearer. So, for example, integrate. So my first one here, dx.
Sorry, Professor.
Sure.
Can you just go back to just 1 second?
Sure. Yeah, not a problem. Yeah, definitely. Anytime I change the slide and you guys are not ready, because I can't see your faces and I can't see you writing, definitely let me know. And I have no problem going back and waiting for you guys.
Okay, I'm good, thank you.
No problem. Anybody else need me to wait? No? Okay. I'll get a piece of candy here from my candy jar that's on my desk. Okay. This way. My mouth doesn't get all dry as I'm talking. Okay. So, the first problem we're going to do is... Oh, I just picked up a butterscotch because I forgot to refill. My new favorite right this second is root beer barrels. And I have a whole bag of them, but they're out in the other room. So I forgot to bring it in. But yeah, I know, I feel bad. Like, I have candy in my office all the time. And so I can't be like, hey, come to my office and get candy. And I can help you with calculus, right? Okay. So our problem here is dx over x squared square root of x squared plus 1. And I'm going to go back here. Let me copy this. And I think I can shrink it. Yep. Okay. So we'll just let this live up here. I'll copy it for the future. Okay. Oh, do I know if the fall semester will be online as well? I can tell you that what I know about the math department for the fall. So the math department for the fall right now, we're planning to have we're planning to have completely online classes. So like that's not what our class is, right? While our class is completely online, it's known as web remote because it has the actual meeting times and like I'm live lecturing as if we were in the classroom. So the math department in the fall is planning on offering web remote classes, so like our class right now, completely online classes, so like ones where, you know, nobody's like lecturing live to you, and then also having in-class classes. So they are planning on, like, whereas right now there's like barely any in-class classes, we are planning on more in-class classes, with the idea that, you know, if the situation ends up needing to be some of those in-class classes need to be web remote, they can be. But we tried to do a mix of all the 3 different delivery styles of classes. So if you're like, I hate this and I want to be back in the classroom, you should be able to find a course back in a classroom in the fall. I will not be teaching Calc 3 in the fall. Yeah, I find online classes to be terrible too. So I'm trying my best here to make it the best we can, but this is not my preferred way to teach either. So I totally understand. Yeah, I haven't taught Calc 3, in years. So Calc 3 is not my jam. It's not my favorite one. So I usually avoid Calc 3. Any other questions? Yeah. Okay. So, back to the problem at hand here. If you look at this problem, right, there's no way for me to do a U substitution, right? Usually, Julio, I don't know. It would depend on who took the class and is teaching it. So I don't know off the top of my head whether discrete math and higher would be in the classroom or in this web remote format. I believe it would be one of those two. It wouldn't be completely online all by yourself. but I don't know which of the other two formats it is. No. My classes for the fall are all much lower level. So they're lower than calculus. Unfortunately. So this problem here, if I tried to do a U substitution, right? If I tried to look at the stuff underneath here, the stuff underneath the square root sign here, I would end up, if I let that be my U, I would need a 2x as my du, and I don't have that x. I have this other x squared down here on the bottom, and so that's messing things up. And so this is not a candidate for just regular old substitution. But if you notice, it is of this form, a squared plus x squared, right? So remember the a squared plus x squared, you could have a squared plus x squared, or you could have it be the other way around, x squared plus a squared, right? And so that's what we have. So this here, right, is of that form, x squared plus a squared. And so in this case, my a is what? 1, right. Okay, so when I have x squared plus a squared, we do the substitution to let x be equal to a tangent theta. So we're going to let x be equal to, our a is a 1, so 1 tangent theta. Now, I put the 1 there since this was the first problem. If it's a 1, you don't have to write the 1, right? So really, x is just tangent of theta. Okay. So once I make that substitution, there are two things that I'm going to do straight off the bat. One is I'm going to look at my problem and I'm going to figure out all the pieces I need to plug in, right? So if we look at what I have here, I have a dx, so I'm going to need to plug in for dx. So I can find dx. So dx is going to be, we're just going to take the derivative of that x equals tangent theta. So what's the derivative of tangent theta? Secant squared theta. And then we have to tack on that d theta because we're doing that differential. If you notice, I need, for that pink part, where that pink is circled, I need to figure out the square root of x squared plus 1. So the square root of x squared plus 1 is going to be the square root of x's tangent. So it's going to be tangent squared theta plus 1. So all I'm doing is I'm taking my x, which is tangent theta, and I plugged it in here for this x. So instead of x squared plus 1, x is the same as tangent theta. I get tangent squared theta plus 1. Does anybody remember what tangent squared theta plus 1 is? Yeah, so tangent squared theta plus 1 is secant squared theta. So remember, again, that's on that sheet I gave you. So if you don't remember that handout we talked about last time, that identity is on there for you. So this is going to be the square root of secant squared theta. And that's kind of nice, because what happens with the square and the square root there? The square and the square root disappear. They cancel each other out. Okay, so my square root part actually simplified down to this nice little secant theta. It's pretty nice. I also have an x squared. So my x squared is going to be tangent squared theta. And so if you look here, I took care of the dx part. I took care of the x squared part. I took care of the square root part. So I'm ready to go. I can plug all those pieces in. The second thing we're always going to do is we're going to take our substitution, and from it we're going to draw a triangle. And the reason we're going to do this is because we're going to need this triangle at the end. So basically what we're doing is we're taking a problem. So I think of it like I have a problem. Say my problem was in Spanish, and I didn't understand how to solve it. Like, I'm not a native Spanish speaker. So for me to really be able to figure out what I want to do, I translated my problem. So say I translated my problem into English. We work the problem in English, but at the end we have to go back to Spanish, right? So maybe I'm working with someone who's in Spain on a math problem. And so they send me stuff in Spanish. I translate it to English. I do my part in English, but then I have to translate my answer back to Spanish to send back to this person I'm working with. So because of this, we're going to need a way to go back to x's. And the way to go back is using this triangle. So we're drawing the triangle now, but we're not really going to use the triangle until the very end of the problem. Okay, I just say just draw the triangle now when you're beginning. But if you want to wait and draw it at the end, you can. So we're going to draw a triangle. And we're basing our triangle, so here's my angle theta. We're basing it off of the fact that x is equal to the tangent of theta. So if you remember, tangent is opposite over the adjacent. Why does x squared equal tangent squared? Okay, so x squared equals tangent squared because remember, x is equal to tangent. So if I square this side, I get x squared. If I square this side, I get tangent squared. Does that help? Yeah, so I'm just basically taking that substitution I made, and putting it into all the places. So x equals tangent theta, so you can think of this as x over 1. And so remember, tangent is opposite over the adjacent, so the opposite side of this triangle is going to be the x, and this adjacent side is going to be 1. And then I can use Pythagorean theorem to find the hypotenuse, right? So a squared plus b squared equals c squared. So 1 squared plus x squared equals c squared. So 1 plus x squared equals c squared. So c is going to be the square root of 1 plus x squared. And it's technically plus or minus, but we're just going to worry about, when we're talking about the hypotenuse, we're always going to take the positive case. So this is going to be the square root of 1 plus x squared. Questions on anything I did so far? Can I scroll down a bit? Sure. Does that help? No problem. Yeah, I'll try to make sure I don't write that far down on the next problem. Other questions? I'm going to show you. So we haven't used any of these pieces yet. So hopefully that question, Thor, will make sense in a minute. If it doesn't, then ask it to me again once I use it. So I haven't solved the problem at all yet, right? I've just kind of set stuff up for myself. So now what we're going to do is we're going to go back to this original problem, and we're going to make our replacements, right? So I have the integral sign. dx, right? I said dx is now secant squared theta d theta. So instead of the dx, I'm going to write secant squared theta d theta. On the bottom, instead of x squared is tangent squared theta. And then instead of the square root of x plus 1, right, this part here, I have secant theta. So now my problem looks like this. Questions on what I did here so far? Okay, so now it's kind of nice when my secants would cancel out, right? So this secant cancels out with the squared. So I really have the integral of secant theta d theta over tangent squared theta. Now, unfortunately, secant theta over tangent squared theta is not something that I just know how to integrate. So if I have a bunch of stuff and it's not sines and cosines, and it's all kind of all over the place like this is, I actually change everything into sines and cosines. So that's what we're going to do next. We're going to rewrite this and change it into sines and cosines. So secant is 1 over the cosine of theta. So I have 1 over the cosine of theta. Tangent squared is going to be sine squared theta over cosine squared theta d theta. And I have a fraction, divide by a fraction, so we're going to do keep, change, flip. So I get 1 over cosine theta times cosine squared theta over sine squared theta d theta. And this helps me out some because now the cosines can cancel. So now I've got the integral of cosine theta over sine squared theta d theta. So now I've got a nice little problem going on. Questions about anything I did so far. So we're still not done. Still a little bit away from being done. But we've gotten it to this part. Yeah, so at this point we're going to use substitution. So we can make the u, what should we try making for our u? Yeah, sine. So if we let u be equal to the sine of theta, then du, so the derivative of sine is going to be cosine theta d theta. So that's super nice because that's exactly what I have. So this is going to become the integral of 1 over u squared du, which is the integral of u to the negative 2 du. And if I integrate u to the negative 2, I'm going to come all the way up here. What do I get? I get, okay, so it's not you can only do the natural log if it's a u to the first power. So anytime you have a power that's not 1, it's not a natural log anymore. You have to rewrite it this way and then just add 1 to the power and divide by adding 1 to the power. It's only 1 over u or 1 over just one single x or 1 over one single y. Those are all the ones that are the natural logs. So yeah, so this is going to become u to the negative 1 over negative 1 plus c. Or I could write this as minus 1 over u plus c. Okay, so now I have to go back from my u substitution. So my u was sine theta. So this is going to be negative 1 over sine theta plus c. Okay, so I did the integral. My integral had a u substitution. I did the u substitution. I'm back to thetas, but remember, this is like me solving the problem in English. I still have to translate it back to that original Spanish, right? To be able to say, send my answer. My original problem here started in x's. So I have to get back to x's. And right now, I'm stuck in thetas, right? The thing I have right here is the sine of theta. And this is where that triangle comes into play. So if you look at this triangle here, we can use this triangle to figure out what the sine of theta is. So what is the sine of theta from that triangle? So it's the opposite side over the hypotenuse. So we're going to have negative 1 over. The opposite side is x. The hypotenuse is the square root of 1 plus x squared. And then again, since I'm dividing, right, this is negative 1 times square root of 1 plus x squared over x plus c. Or I can put them together. Negative square root 1 plus x squared all over x plus c. So it's kind of a cool little problem, right? You started with something we couldn't integrate. I changed it into trig functions, which then actually made it so that I could integrate it. And then I integrated it, and then I used that triangle to go back to x's. So that's the general gist, right? Almost every single one of these problems is going to be that exact same thing. Question. And I want to give you guys a minute to copy stuff down, because I know there's a lot going on there. Okay, so I used x over the square root of 1 plus x squared because I needed the sine of theta. So if I look over here at my triangle, here's theta. Sine is the opposite x over the hypotenuse square root of 1 plus x squared. So I'm using this triangle to figure out the sine value. So sine is opposite over hypotenuse. So I'm using the opposite side x over the hypotenuse square root of 1 plus x squared. Does that help? Good. Other questions? Yeah. Should we try another one? Does anybody need me to wait before I change the page? Sure. Oh, I don't know if Sandra's yes was to turning the page or not turning the page. It might have been to my previous question. So I'll try again. Anybody need me to wait to turn the page? No? Okay. Okay, so let me... Okay, so remember, this is what we're dealing with, our substitutions there. Okay, so... this is B. The integral from 0 to 1 of dx over 4 minus x squared all to the 3/2 power. Okay, so again, right, it looks like you'd like to make a substitution. You have a bunch of stuff all raised to the 3/2 power, but I can't actually make that substitution because if I let u be the stuff, I don't have the x that I need for the du. So it's going to be one of these trig substitution problems. Which form do I have? Do I have the a plus x squared, the a squared minus x squared, the x squared minus a squared? Yeah, so I have the a squared minus x squared. So in this case, my a is what? Okay, so you want to be a little careful, right? Remember, this is matching up with a squared minus x squared. So it's not that a is 4, a is 2, right? Because you want a squared to be end up being 4. So in this case, a is 2, right? So we can even kind of write that down here to remind ourselves here. A is 2. So we're going to substitute. We're going to let x be equal to a sine theta. So it's going to be 2 sine theta. Questions on how I got that? No. Okay, and then I need to find my pieces, right? So I'm going to have to plug in for dx. So dx is going to be what? Mm-hmm. 2 cosine theta. So 2 cosine theta d theta. The other thing I need to plug in, there's only kind of one other chunk thing, right? The other thing I need to plug in is 4 minus x squared to the 3/2 power. So this is going to be 4 minus, so x squared, so it's going to be 4 minus 2 sine theta squared, all raised to the 3/2 power. And so it's going to take us a little bit of work, right? I should say you can do this work either here on the side, like I'm doing today in class. I think my answers for the homework of this section, I do the work just within the integral sign. It doesn't really matter where you do it. So you'll eventually get to the same thing I do. So this is going to be 4 minus 4 sine squared theta to the 3/2 power. And then if you notice, both of those pieces have a 4. So I can factor that 4 out. So I have 4 times 1 minus sine squared theta to the 3/2 power. So questions about anything I've done so far? No. Okay, what is 1 minus sine squared theta? Cosine squared theta. So this is going to be 4 cosine squared theta to the 3/2 power. And so what's nice about that is now that everything is multiplied inside, I can just distribute that exponent, right? So we're going to end up with 4 to the 3/2 power, and then I have cosine squared theta to the 3/2 power. So in the cosine squared theta, so remember what 3/2 power means, because I think a bunch of people ran into this on the test, right? So 3/2, right? It's saying I'm cubing something and then I'm taking the square root, or you can do the square root part first. So you could take a square root and then cube something. So if I square cosine and then I take the square root of it, that undoes each other. So the second piece here is just cosine cubed theta. And then here, if I take the square root of 4, what's the square root of 4? 2. And then if I raise 2 to the 3rd power, what do I get? 8, right. So this turns out to be 8 cosine cubed theta. So it takes some algebra. These problems definitely take some algebra. They are good at getting at your algebra skills.
How did you get the cosine cubed again? Did you multiply the 2 and the 3/2 or add it?
Yeah, I multiplied the 2 and the 3/2. So 2 times 3/2, the 2's would cancel, and you just have that 3. So you would get that cosine cubed.
Thank you.
No problem. Other questions? Okay, so I've gotten all the pieces I need to plug in. The other thing, remember the 2 things you do at the beginning, get all the pieces you need. And then the second thing that we're going to do is we're going to use this first piece here to draw our triangle, right? So remember we have x is equal to 2 sine theta. And in all these problems, you want to solve for the trig part. So if I divide both sides by 2, we get that the sine of theta is equal to x over 2. So if I draw my triangle, the sine of theta, so remember sine is opposite x over the hypotenuse 2. And if you use Pythagorean theorem, right, so a squared plus b squared equals c squared, right? We're going to have a squared plus x squared equals 2 squared. So a squared plus x squared equals 4. Or a squared is going to be 4 minus x squared, which means this part here is going to be the square root of 4 minus x squared. Questions? No? Okay. So, I found all my pieces. I made my triangle. So now I can plug in, and so this is going to be equal to, now I have those limits. Those limits on here are they're x limits. So I'm just going to keep reminding myself of that. I'm not going to change the limits. I'm just going to wait till we're back to x's and then plug them in. I know I'm a big proponent of, if you do a u substitution, change the limits. However, these problems are just long. You'd have to change your limits a bunch of times. So in this case, to me, it's just not worth it. We're just going to wait. But we don't want to forget about them. So I'm going to write them as x equals 0 and x equals 1. I'm writing them as x equals 0 and x equals 1 to remind myself, to jog my memory, hey, don't plug these in until you're back at x's. Okay, so we're not going to plug them in for thetas. We're not going to plug them in for any u's if we happen to end up with u's in this problem. We're going to wait till we're back to thetas. Okay, so I know that dx is 2 cosine theta, d theta. And we know that the bottom, which was 4 minus x squared to the 3/2, is 8 cosine cubed theta. So my 2 and my 8 would cancel and give me a 4. This cosine is going to cancel one of those cosines and leave me with 2 of them. So I'm going to have the integral from x equals 0 to x equals 1 of d theta over, and I'm going to pull this 1/4 out in front just because, so it doesn't get in our way here, over cosine squared theta. Questions about anything I've done so far? Okay. Anyone want to take a guess what we should do with that? D theta over cosine squared theta? Okay. All right. So.
Change it into sorry.
No, go ahead.
Can you change it into secant squared?
Yeah. So, okay, so some people are saying make a u substitution. If you tried making a u substitution, you're going to run into problems because you would, if you tried letting u be cosine theta, du, you're going to need a sine theta, and we don't have any. But remember, 1 over cosine is secant. So this is really, we have 2 cosines in the bottom, so this is really just 1/4 the integral x equals 0 to x equals 1 of secant squared theta d theta. So we technically are bringing the cosine up as cosine to the negative 2 power, but that is just secant to the squared power. Questions?
And then we know that from the handout sheet, right?
I don't know if I put that on the handout sheet. So that's just like, that's one of those like basic trig identities, that 1 over the cosine of theta is the secant of theta. Right. Remember the other ones are basically 1 over the tangent of theta is the cotangent of theta. 1 over the sine of theta is the cosecant of theta. So those are kind of just like 3 basic reciprocal identities back from Math 127.
Okay, thank you.
No problem. But yes, so the helpful thing about changing it into the secant squared is we actually just can integrate secant squared. So the integral of secant squared, as Sandra said, is tangent. So this is just becomes 1/4 the tangent of theta evaluated from x equals 0 to x equals 1. So I've made it back to thetas, but I have to now use that triangle to get back to x's, right? So I'm looking for the tangent of theta. So I'm going to come down here to my triangle. Tangent is opposite x over adjacent, square root of 4 minus x squared. So this is going to be 1/4 times x over square root of 4 minus x squared. And now that we're back in x's, we can just evaluate that between 0 and 1. So we're going to plug in the 1. So we've got 1/4 times 1 over the square root of 4 minus 1 squared minus 1/4 times 0 over the square root of 4 minus 0 squared. So this second piece here, this all goes to 0. So I'm left with 1/4 times square root of 4 minus 1 squared. Oh. Anybody else can't hear me? Or can people hear me still? Did I mute myself?
I can hear you too.
Okay. Okay. Sandra, oh, well, she can't hear me. She's not going to say it. So let me type this. I would leave and come back if the audio is still out. So we end up with square root of 4 minus 1 squared is square root of 3. So I get 1 over the square root of 3. So this is just 1 over 4 root 3. Questions? I know people have questions because when I teach this in the classroom, people have questions. So if you have a question, there's nothing wrong with asking it. No. So when you solve for A, B, or C in the triangle thing, will always be what you substitute for in the beginning. Okay, it's not always exactly, but it's always the same form. Yes. So, it's not, once in a while, like your problem might have a square root of, say, or your problem could have just had an a squared minus x squared, not under a root. And in the triangle, you might have, you would end up with a square root, but it is going to be of that same form. So if your original problem has an a squared minus x squared, when you solve in the triangle, you're going to end up with an a squared minus x squared. Does that answer your question, Kobe? Yeah, so it's kind of nice. It's kind of like a little bit of a double check that you did something correct. Other questions? The tangent, are you talking about this tangent here, Thor? Okay, this tangent came because the integral of secant squared is tangent. So remember, the derivative of tangent is secant squared, so the integral of secant squared is tangent. So Josh, so if the problem were to start getting extremely confusing, then it's safe to assume we subbed something out wrong. Yeah, like you should get something that is easier to integrate. Easier being loosely interpreted, right? Because easier still might require a lot of work. But if you get like a giant mess that like nothing is canceling out, nothing is like making it look nicer, then yeah, you did something wrong. Does that answer your question? Other questions? And I have more examples, so we're going to do more problems here. Yep, these problems can turn into problems of the last section. As a matter of fact, we're going to get one of them right now. So yeah, that's why we do the trig integrals first, because technically any of these problems can turn into the trig integral problems. Yeah, I know. But they're cute. These are cool. I think it's cool that you start with a problem that has no trig in it. You add trig into it, and it actually makes it easier to integrate, right? When does that happen? Not that often. Excuse me. All right. So let's try another one here. Yeah, I agree. Yeah, you do have to practice them, but they are kind of fun. Okay, so C... we're going to do the integral of the square root of y squared minus 25 divided by y cubed dy. And so remember, here's our substitution. Okay, so again, if you tried to do regular old substitution on this problem, it's not going to go well for you. So which form is this problem here? Yeah, x squared minus a squared. And what is my a? Yeah, so the a is 5. So we're going to we're going to use x squared minus a squared. So it's going to be a secant. So it's going to be a secant theta. So in our case, that's going to be 5 secant theta. So we're going to and in this case, instead of x, right, our problem didn't start with x's. So we're going to have a y. So let y be equal to 5 secant theta. And then we're just going to find all the pieces that we need. So I usually find the dy next. So dy or dx, depending whether you have x's or y's, I find that part next. So what's the derivative of 5 secant theta? Yeah, 5 secant theta tangent theta. So 5 secant theta tangent theta, d theta. Okay, and then I need to figure out the other pieces. So one of the pieces I need to figure out is a y cubed. The other piece I need to... whoops. Let me pull this up because I accidentally end up leaning on the bottom there and going back pages. So the other part I need to figure out, so I can figure out the y cubed. The other part I need to figure out is the square root. So if we start with the y cubed part, just because it's the easier one. So y cubed is going to be 5 secant theta cubed, or 5 cubed is 125 secant cubed theta. Are we okay with everything I did so far?
I missed the part where you did the y cubed equaling to that. You just did that because there's a y cubed in the denominator, and you cubed everything. Got it. Okay, thank you.
No problem. Any other questions? Okay, the other piece I need is that will A always be... No, no. A is not always a perfect square. I think I have one that's not a perfect square. Oh no, all of mine... Well, I'll show you what to do if A is not a perfect square. So if you had... Let's say you had say you had y squared minus 3, right? And you might say, oh, well, it's not a perfect square, so I don't have, like, x squared minus a squared. Technically, you can always rewrite something that's not a perfect square as, you could think of this as y squared minus the square root of 3 squared. So you can always turn it into a perfect square. And so in this case, a would just be the square root of 3. Does that help, Robert? Yeah, so if you end up with something that's not a perfect square, you can definitely turn it into a perfect square. Okay, so the other piece we need to figure out is the square root of y squared minus 25. So it's going to be the square root of 5 secant theta squared minus 25. And 5 secant theta squared, this is going to be 25 secant squared theta minus 25. And so this should always work out for you. You should be able to factor something out and then replace using one of the Pythagorean identities. So this is going to be the square root of 25 times secant squared theta minus 1. And remember, secant squared theta minus 1 is tangent squared. So this is going to be the square root of 25 tangent squared theta. And so now that everything's multiplied, I can just take the square root of both of those pieces. Square root of 25 is 5. Square root of tangent squared is tangent theta. Okay, where did I lose you, Josh? Okay, so, so you don't know how I got this step? Okay, but you're okay with this first step? Okay, so all I did to go from the first step to the second step is I squared both of these things. So I have this quantity squared, and since they're just multiplied, I can square each piece. So 5 squared is 25. Secant squared is secant squared. Okay, so the third step, no problem. So to go from this step down to this step, I noticed that both of these pieces have a 25 in them. So I'm factoring the 25 out. So when I take 25, so think about it, if I took this 25 and I distributed it, I would get 25 secant squared theta, that's the first piece here. And then 25 times what would give me minus 25. 25 times negative 1. So that's how I pulled that 25 out. Does that help? Yeah, yeah, the parentheses definitely help. Other questions? No. Okay, so I have all my pieces. The other thing I need to do is draw my triangle, right? So my triangle is coming off of this part here. So if I come down here, we know that y is equal to 5 secant theta. If I divide both sides by 5, I get y over 5 is equal to secant of theta. Remember, secant is just cosine flipped over, right? So when I go to put this on my triangle, here's my theta, it's the hypotenuse, y, over the adjacent 5. And then again, use Pythagorean theorem, a squared plus b squared equals c squared, right? So 5 squared plus b squared equals y squared. So b squared is going to be y squared minus 25. So this side's going to be the square root of y squared minus 25. Questions?
Just really quick, Dr. Gorman.
Mm-hmm.
For the triangle, how do you determine like the placement, which one's
So, sure. Well, A and B, it doesn't matter. Like, you could call this A or you could call this B. So A and B have to be the legs of the right triangle. C is always the hypotenuse. How I determined that the y goes here and the 5 goes here is that's based off of secant. So remember, secant is the hypotenuse over the adjacent. So the hypotenuse is that longest side, so the hypotenuse has to be the y, and the adjacent then would have to be the 5. Does that help?
Okay, so I guess it's safe to assume, so C is always going to be the hypotenuse, and A and B are basically fair game?
Yeah, C is always, as long as you make sure you put C as the hypotenuse, it doesn't matter what one you call in it, A, and what one you call B.
Okay, thank you.
No problem. Other questions? No? Okay, so now we're at a point where we can plug in, right? I'm just going to section this stuff off here so we know that's not part of the problem we're dealing with. So if I plug in here, okay, our square root was 5 tangent theta. dy was 5 secant theta tangent theta d theta. And y cubed was 125 secant cubed theta, right? So all I've done is plug in for each of my pieces. And so we can cancel some things out, right? On the top, I have 5 times 5, right? I have 1 5 and another 5. So that would end up being 25. And 25 goes into 125 5 times. So these two 5s on the top cancel out on the bottom to just leave me with a 5. Because 5 times 5 is 25. 25 goes into 125 5 times. I also can cancel out my secant on the top with one of the ones on the bottom. So what I'm left with is, to make my life a little easier, I'm going to pull the 1/5 out in front. And I have an integral on the top. I have 2 tangents, and they're multiplied together. So it's going to be tangent squared theta. And on the bottom, I have secant squared theta d theta. And tangent squared theta over secant squared theta if you remember from last class, it's not tangent times secant. So if I had tangent and times secant, then I could try to do one of those things from last class. So if you remember, if you had any other kind of situation going on, I said to change it into sines and cosines. So we're going to change the tangent squared into sines and cosines, and we'll change the secant squared. So this is going to become 1/5 the integral. So tangent squared is sine squared theta over cosine squared theta. All over secant is 1 over cosine squared theta d theta. And again, I can rewrite that keep, change, flip. So we've got sine squared theta over cosine squared theta times cosine squared theta over 1 d theta. And that's pretty nice because the cosine squareds would cancel each other out. So this is going to be 1/5 the integral sine squared theta d theta. Okay, questions? Right, we still haven't integrated yet. All we've done is a bunch of algebra. Okay, so I need to integrate sine squared. Does anybody remember from last class how we're going to integrate? All I have is a sine squared. What we're going to do to be able to integrate that. Yeah, so we have to use a half angle identity. So this is going to be 1/5 the integral of 1/2 1 minus cosine of 2 theta d theta. So I can pull the 1/2 out in front. So 1/10 the integral of 1 minus the cosine of 2 theta d theta. And now I can actually integrate that, so I end up with 1/10 times. So what's the integral of 1? Yeah, so the integral 1 is theta, right? Because the variable I'm dealing with right now when I'm integrating is theta. So it's going to be theta minus, to integrate cosine of 2 theta, you could either do a U substitution or you could use my trick. So it's going to be 1/2 the sine of 2 theta plus c. Okay, so I've made it back to thetas. Now I just have to make it from thetas back to x's, which is actually a little bit tricky here because sorry, I'm reading a message. Yeah, so Brian sent me a message and asked me a question. So I'm just going to answer rather than type an answer back to him. Yes, I gave them both. So yeah, you could have done something different than what I'm doing. But there's a reason I'm doing what I'm doing. Okay. So questions about how I got to this part before we go back to x's and we talk about that. No. Okay. So I have to somehow from my triangle get theta, which it's not like I can just read what the angle exactly is off. But if you remember from trig, I have here that the secant of theta is equal to, how did I get the 1/2 on the third? Okay. So, on the third to last line. Okay, this here, the 1/2 1 minus cosine of 2 theta, that is the half angle identity. So that's what we were doing last class. So it's just a straight up sine squared theta is actually equal to 1/2 times 1 minus cosine of 2 theta. And that identity is on that sheet that I posted last class. No problem. Any other questions? No. Okay, so over here, I know that y over 5 is the secant of theta. I want to figure out what secant is. So if you remember from trig, if you are trying to get what the angle is, you can use an inverse function. So theta is equal to the inverse secant of y over 5. So if I take the inverse secant of both sides, the inverse secant of the secant drops out and I just get theta. And then the other side I get this inverse secant of y over 5. So I can plug back in for this theta now without a problem. Now I know what theta is. The harder thing is that here I have a 2 theta and my triangle here is only in terms of theta. Going from theta to 2 theta is not, it's not that you just multiply stuff by 2. I don't know the stuff for 2 theta. So I actually have to use another identity to replace the sine of 2 theta to get it back in terms of thetas. So to do that, we're going to have 1/10. I have a theta minus 1/2. So we're actually going to use the double angle identity, which says that the sine of 2 theta is 2 sine theta. I need to move this over a little bit so I can make it fit. Okay, so this is a 1/5. Oops, 1/10. Nope. Let me just rewrite that. Okay, so I'm coming up here. So this is equal to 1/10 theta minus 1/2 2 sine theta cosine theta plus c. So I basically replace the sine of 2 theta with the identity that the sine of 2 theta is 2 sine theta cosine theta. And here my 2's would cancel. So I've really got 1/10 times theta minus sine theta cosine theta plus c. And sine theta I can read off of my triangle. Cosine theta I can read off of my triangle. So this is going to become 1/10. Theta, we said, is the inverse secant of y over 5 minus, I'm just going to write it down here so I have enough room. The sine is square root of y squared minus 25 over y. The cosine is 5 over y plus c. And you can just leave it as that mess. You could multiply it together if you wanted to make it a little bit nicer, but you don't have to. Questions? So there's a lot in that problem, right? So the idea is like when you get to the end and you need to go back to x's, you got to make sure it's just of single thetas. So that's why we had to use that extra identity. And that's why I put all those identities on that sheet.
Dr. Gorman, can you just explain the last 2 steps that you did? How did you jump from the negative
from here
theta, cosine theta to secant?
From here to here?
Yes, ma'am.
Okay. So over here, so the first part here, this theta to get the inverse secant, the thing I did here is I went back to that original, the part I used to make the triangle, right? So the thing I used to make the triangle, I know that the secant theta is y over 5. So from my triangle here, right, I'm trying to figure out theta. So to get theta, to untrap your theta, you have to use an inverse trig function. So back from math 127. So that's where I went from this step here to here. So if y over 5 is equal to the secant of theta, theta is equal to the inverse secant of y over 5. Does that make sense?
Yes. Yeah.
Oh, okay.
I didn't see that.
Yeah, no problem. Yeah, I know. There's a lot of moving pieces on these. So this part here, that's how I got this first piece here. Then for sine theta and cosine theta, I went back to the triangle. So sine is opposite, so square root of y squared minus 25 over the hypotenuse y. And then, so that's how I got this first part. And then cosine is adjacent, 5, over the hypotenuse y. So that's how I got this second part. Does that...
Thank you so much.
No problem. Other questions? Yeah, they're long. They are long problems. The pages of my notebook aren't big enough. I know. When I took Calc 2, when I was in college, I remember at the end of the semester having to just take, I think I went through 2 notebooks first off. And when I was towards the end of my second notebook, I'm running out of room and there was like 2 classes left. I'm like, this is ridiculous. I'm not buying a third notebook. And I remember just taking sheets of paper and stapling them to the cardboard back of my notebook and like doing more problems on them. Yeah. And Brian had me, so. Yeah. Other questions? No. Okay, should we try another one? All right. So I think this is D. So we have the integral of 5 over the square root of 25x squared minus 9 dx. So this one looks a little different, right? It kind of looks like what form? Okay, it kind of looks like x squared minus a squared, but the problem is it's not just x squared, right? It's 25x squared. So that 25 presents a little bit of a problem. So we're actually going to think about this as the integral of 5 over the square root of 5x quantity squared minus 9 dx. And so so rather than just an x squared this time, I have a 5x, right? So before, when we had x squared minus a squared, what did we sub? We would say that x was equal to what? Not tangent, but x was equal to which trig function? Yeah, a secant theta. So in this case, rather than say x is equal to a secant theta, I don't have just an x, I have a 5x. So we're going to say 5x is equal to, what's my a in this case? 3, right? So 5x is equal to 3 secant theta, right? So since I don't just have an x, that's why I'm doctoring it up just a tiny little bit, right? So instead of saying x equals a secant theta, since I have a 5x, I'm going to say 5x equals a secant theta. Questions? No. Okay, so I need dx. So where before I would just say, oh, the derivative of x is dx. The derivative of 5x is 5 dx. And then this is going to be 3 secant theta tangent theta d theta. And that works out kind of nice because if you notice on the top, I have a 5 and a dx, right? So 5 dx, it works out pretty nice. If I didn't, I would have to kind of put that 5 in to help me out. You could divide, you could definitely do that. You could divide the 3 secant theta by 5 and then find dx that way. That's totally fine. I didn't do that because I know that up here I already happen to have 5 dx. So I'm just going to replace that 5 dx with this stuff here, the 3 secant theta tangent theta d theta. But if you wanted to solve that first part for x, you could totally do that. The other stuff I'm going to need here is I'm going to need a square root of 5x squared minus 9. So this is going to end up being the square root of, and I'm going to, wait a minute. I'm going to move this over just because I want to leave myself enough room so I can make it fit on one page here. So this is going to be the square root of, so 5x, remember, is 3 secant theta. Okay, so how does 5x equal 3 secant theta again? Okay, so I'm using, remember our form is if I have x squared minus a squared, it's x equals a secant theta. Using an x is kind of a simplified way of saying this, but basically you can think of this if I have a bunch of stuff squared minus a squared, I'm making the substitution that, the stuff is equal to a secant theta. So in our case, we had 5. So in our case, we had 25x squared. So this is 5x squared minus 9. So my stuff is a 5x. So you can think of that x like stuff. Other questions? No. Okay, so remember 5x is the same as 3 secant theta, so this is going to be 3 secant theta squared minus 9. And 3 secant theta squared is 9 secant squared theta minus 9. Factor out the 9. 9 times secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. So I have the square root of 9 tangent squared theta, which is going to end up being 3 tangent theta. Questions? No. Okay, and then I'll use a different color here since I've already used pink so much. We're going to use this to draw our triangle, right? So remember 5x equals 3 secant theta. If I divide both sides by 3, 5x over 3 equals the secant of theta. And remember secant of theta is the hypotenuse, 5x, over the adjacent 3. So a squared plus b squared equals c squared. So 3 squared plus b squared equals 5x squared. So 9 plus b squared equals 25x squared. So b squared is going to be 25x squared minus 9, which means this side's going to be the square root of 25x squared minus 9. Questions? Okay. So now I can plug into all the stuff, right? So the 5dx, that part that I've circled in pink, we're going to replace with what 5dx is. So 5dx is 3 secant theta, tangent theta, d theta. Kind of go around here. All divided by, that whole square root was just 3 tangent theta. And it's pretty nice because my tangent thetas cancel out, my 3's cancel out, and I'm just left with the integral of secant theta d theta. And secant theta is one of those integrals we talked about last time, right? The integral of secant theta and the integral of secant cubed theta are just ones that I gave you on that sheet. So the integral of secant theta is just the natural log of the absolute value of secant theta plus tangent theta plus c. So, this problem actually turns out to be pretty nice, right? Because it didn't take a lot of work to integrate it. A bunch of stuff dropped out. So it was actually really a pretty nice problem. We're not done yet because remember I have to go back to x's. But that's all I have to do is I just have to figure out what, based from my triangle, what secant theta is and what tangent theta is. So this is going to be the natural log of the absolute value. Secant theta is 5x over 3. And tangent theta, again from the triangle, is opposite. So square root of 25x squared minus 9 over the adjacent, which is 3, plus c. And you can leave it like that. If you want to make it into one fraction, you can. If you want to make it into one fraction and then you want to split the natural log apart, you can. But I'm just going to leave it like that. Questions? Yeah, that one was actually a pretty nice one, right? It fits on one nice little page. Okay. So I have one more example to do, which we'll actually do next class. The example is what's called an initial value problem. And it actually is, like, if you were to go, you can start and do all of the homework problems except for the very last one on the homework for this section. So if you want to look at the homework, totally you can. The homework for this section will be due next Monday. The homework for the next section we're going to do, that's going to take us more than just next class. So it won't be due the following week. So there's only one thing due. So I want to talk about the test for a couple of minutes, and then I kind of want to show you a couple things on Canvas. So let me talk about the test first, since I don't have to, I'll leave this up in case anybody's still copying things. Okay, so first off, I graded your tests. The test, if you go into Canvas and you look at your tests, I made marks on your test. So I wrote notes, I wrote things that you did wrong, stuff like that actually on your test. So you can see I put marks besides a grade. There's a grade, but if you actually click on, you should be able to click on your uploaded file and actually see how I corrected it. The tests were kind of a little all over the place, right? So some people did really well. Some people did not do so well. Some people did in the middle. They were kind of all over. They were more all over than tests usually are in Calc 2. Okay, so usually when I teach Calc 2, the first test, the vast majority of people usually do really well on the first test because it's covering stuff from Calc 1 primarily, and then just one topic in Calc 2. So it's usually not the first test that people struggle on. I understand that a lot of you might have taken Calc 1. I don't know what the average is. I don't actually usually calculate the average. I know a lot of people might have taken Calc 1 like last semester, or it might have been even longer because of that. And I understand it's COVID and it's a really odd time, right? And depending on who you had for Calc 1 and how they did stuff, you may or may not have understood some of the stuff from Calc 1 as well as you should, or things like that. So, I am offering everybody in the class the following opportunity. Okay, so so basically on the final exam, there will be problems on the final exam that are similar to problems from this test. So on the final exam, I will put at least the derivative problem. There will be some just regular use substitution problems. There will be an integration by parts problem when we get to the final exam. So if on the final exam you can show me that you know how to do those things, you know how to take derivatives, you know how to integrate, you know how to do integration by parts. So basically, you might not have done well on this test, but you can recover because by the end of this class, you're like, okay, now I know what I need to do and I can do it, right? So that's all I really care about is by the end of the semester, you can actually do it. What I will do is if on the final exam, you can show me that you can do those things, right? So there'll be basically 3 problems that are kind of earmarked on the final, 3 or 4 problems on the final exam. And I'll say more about this when we get to the final. That if you can do these 3 or 4 problems and show me you know what you're doing, I will give you back on your on this test half of the points that you lost, right? So if you got, let's say you got a 70 on this test, but on the final exam you can show me you know what you're doing, then if you had a 70, you lost 30 points. So I will give you back 15 of those 30 points. So your test 1 grade would then turn into an 85. Okay. So this is the only test that this is going to happen on, right? So, Calc 2 really depends on you being able to take a derivative, do use substitution, and integrate basic things, right? It's just, it's the nature of the beast. You have to be able to do those things in Calc 2. And so this is kind of your chance to basically be like, okay, maybe I didn't do so great on this test. It's not going to kill me for the rest of the semester. It's not going to just tank my grade for the rest of the semester, but I can recover from this. So it's kind of up to you. If you are one of these people who is I had no idea how to integrate and stuff like that, right? I strongly suggest that you go to Khan Academy and watch their use substitution videos. A lot of people had problems just with regular old use substitution, just with regular old integrating things and regular old taking derivatives of things, right? If you need more guidance than that, like you could send me an email, you could come to my office hours, right? You can go to, so you can do that. You can go to tutoring. Like there are basically like things you can do to help you, but like you're going to have to be able to integrate. So let me show you here too. Let me start sharing this. Oops. And let me share my screen here. Okay, so couple other things that I posted here for you to help you out too. So as you're looking over your tests, if you go to the handout, I did put up the solutions. So these are my worked out solutions for the test. So they're there under the handouts. There's also that trig integrals helpful info. Was what was there from last class. And then the other thing I want to show you from the homepage is I actually put up a bunch of the homework assignments for the next couple weeks. So it's laid out for you exactly what is due, when it's due, right? And I have all the pieces, right? So remember, like the homework that's due next Monday, so that's going to be the 8.3. And like I said, you can do everything but the last problem of it right now. So again, here's the homework, then you upload it, then you unlock my solutions, look at my solutions, then take the self-assessment. So you kind of want to do those in that order. Next class, we're going to do part of 8.5. We're just not going to get through all of 8.5, but we'll get through a fair chunk of 8.5. And then on top of it, we'll start section, then we'll do 410. We'll finish 8.5 and do 410 the next class. Questions. Let me see. Pull up what happened to my chat. So yeah, you can do homework 1 through 9 in what's due on the 15th already. Yeah. So what I went over today in class covers it. And 10 I will do next class. I will do a problem similar to 10 next class. Yep. Other questions? Questions about my whole final exam thing? Does that make sense? What I'm trying to say? So basically there'll be problems earmarked on the final exam. If you can get those problems on the final exam, I will give you back half of the points you lost on the test. No questions? Okay, then have a good one, and I will see you guys all on Thursday.
Thank you, Professor. Have a nice day.
Thanks, you too.
I have a question.
Sure.
Professor Bolton.
Sure.
So, I'm kind of late a little bit, but everything you said makes sense, right?